So thus far, we've talked about some fairly simple cases. 1D models that define either deformation of a bar, temperature variations along the length of a bar, perhaps a chemical potential that would induce a change in concentration. Those problems can be solved by hand. So what we've done is motivate how do we set up a finite element problem based on those types of boundary value problems, 1D boundary value problems. But ultimately, if you want to use finite element, it's much more practical for these complex problems where it's more difficult to get a closed form solution. So if we take a more complicated quote-unquote real system and say, let's first talk about diffusion. So let's say you have an insulation boundary here, insulation on the bottom, and then this is exposed to some kind of chemical environment. Maybe it's relative humidity, maybe it's some type of harsh chemical, and due to your chemical potential, there'll be a driving force for whatever this chemistry is to diffuse into the material. So you'll get these gradients. It'll have some concentration around this point, and there are a few cases where you can solve this in closed form, but once you start dealing with even more complex boundaries, it becomes very difficult to do this in closed form. So this is where finite element is very useful. We've talked about these linear elements. So we set up a 1D model and you linearly vary the solution based on an interpolation. So we linearly interpolate between the nodes of a finite element. But you don't have to use that linear interpolation. And furthermore, we want to set up some kind of formal method to solve these fields and interpolate in between the nodes. So we're going to take a solution of Ux. This may, let's just say this is displacement. It could also be temperature or chemical potential that we've introduced. But this is going to be the solution of some equation, some ODE. And when we do this with finite element, what we do is we don't expect to get the exact solution, but we get an approximation of this solution that's usually pretty good, and we can control how good it is. But ultimately what we do is we define this function phi sub j here, where we're going to sum over j equals 1 to some value that we're going to define later, n, and this function is then coupled with these unknown constants. So these are the constants that we have to solve. It turns out that these constants will be the solutions of, let's say, displacement at every node in the finite element. So we don't know those. That's what we're going to solve based on our equation, based on a set of boundary conditions that are known. Also notice that I have an underline under this x. So what that means is I'm defining this potential. So actually there's no underline here, so this is just a scalar. So this would have to be things like a temperature or chemical potential, but that may vary in 3D. So my spatial coordinate has 3 components given here in Cartesian, x, y, and z, or x1, 2, and 3. Alright, now let's go back to a 1D model. So here's an ODE that's often used to describe a 1D rod. So I may have varying material properties. I can describe varying cross-section areas. I'm going to have some load on the end, I'm defining as Q naught, and internal displacements. A rod with a rod of length L. So my boundary conditions for this particular case is I'm defining U naught here. Typically we'll define this as 0, and on the opposite end I'm defining this flux, which is defined by the derivative of displacement over x at the end times this constant. So in mechanics this would this constant would be your cross-section area times your modulus. This is your strain. So this gives, does that give, yes, that gives the units of force. So this would be in units of newtons. Right? So now the critical part, you should be somewhat familiar with this. It may have a unusual form here, but you should have seen this in some class on ODEs. Now let's talk more specific about how would we implement this in a finite element scheme. So recall, we're going to define these nodal, what I call nodal displacements or nodal solutions, approximating the true solution based on this interpolation function. So these are my unknown constants again. Here's my interpolation function, and I may have some interpolation function for phi naught. So as an example, let's let n equal 2. We have a length of 1, displacement at the left side is 1, and there's 0 flux or 0 force on the opposite end. And let's say that our properties vary linearly along with x. We have this constant c. If I come back up here, this gives an internal force, like a body force inside here, and then this is another body force that we set to 0. So ultimately, excluding some of the physics we'll get into later, we basically want to solve this ODE using the finite element method, subjected to these boundary conditions on the two ends. Okay, so here's what we have. So my nodal solution at point 2, and I'm defining point 2 on the opposite end where x equals L. So I have C1 phi 1, C2 phi 2 plus phi naught. So I am simply summing up this, or expanding this equation for n equals 2. So what we have to do is choose these interpolation functions very carefully to make sure we get a unique solution, right? So we'll talk about this in the next lecture under sections 2.4 and 2.5.